We will start Module 4 talking about atomic forms of energy. Energy is a very important magnitude in chemistry because it will be the fuel that will make things happen, that will motivate change. So it's a very important concept to have both at the atomic and at the macroscopic level. So let's start talking about what energy is and what energy looks like at the atomic level. Energy, the etymology of it just comes from the Greek and it means active or working. We will think of energy, a body will have energy when that body has an ability to perform work. A body will have energy when that system has an ability to perform work. There will be an exchange of energy when that ability to perform work is being exchanged. So at the atomic level, there are two main forms of energy. At the atomic level, there is kinetic energy, and the kinetic energy, if you've taken physics, you may be familiar with this formula in which the kinetic energy is proportional to the mass of the particle and the square of the velocity. The higher the velocity, the higher the kinetic energy, the higher the mass, the higher the kinetic energy. It's pretty straightforward to imagine that a gas with high temperature, high kinetic energy, it will have more energy. The other, maybe more subtle form of energy at the atomic level is what we call potential energy. And the potential energy, unlike the kinetic energy that depended only on the speed, it depends on the relative position of particles that interact. In this graph, for example, imagine when two hydrogen atoms approach to form the hydrogen molecule. They will first attract each other until they reach what we call the bond distance. Okay, if they are too far apart, they will not. They will try to get together. If they are too close, they will repulse each other. If you've taken organic chemistry, you may be very familiar with the different conformations of ethane that you see here. Depending on the relative position of hydrogens, they may hinder each other. So when they are staggered in the position of hydrogens is staggered, it's a lower potential energy. When they are eclipsed, it's a higher potential energy. So let's see what that potential and kinetic energy looks like in a reaction. So I'm going to click on this link and it will lead to a simulation, and it's important to see that this simulation is, as the PowerPoint said, is just a chemical reaction when hydrogen and chlorine react to form two molecules of hydrochloric acid. Well, in this case it would be hydrogen chloride because it's gas. So what does that look like? So first, the green ones is hydrogen, the blue ones is chlorine. As they start moving, they start like shoving each other. And it's important maybe to keep track of the kinetic and potential energy of the whole system. Look here, in red you have the kinetic energy, in blue you have the potential energy, and let's observe what happens both in the simulation, but both in the plot of the kinetic energy. Notice that, let me stop the simulation for a while. Now the system started reacting and molecules got speed, got kinetic energy. Where did that kinetic energy come from? It came from a liberation, if you will, of potential energy. There were some potential energy accumulated in the reactants that now once it reaches products, it gets freed and it becomes kinetic energy. So notice that kinetic energy will keep increasing and potential energy will keep decreasing until they reach, all molecules or most of them reach products. Okay, so it's important to know that in pink you see here the overall energy, so the summation of kinetic and potential, and it's always constant. So that's a little bit the take-home message of this simulation, is that the total energy, and now we're going to call it the total internal energy of a system at the atomic level, is the kinetic energy and the potential energy. And this, the total internal energy, for a closed system at least, is constant. So notice that in the reaction, your system, in reactants, you had a lot of potential energy and low kinetic energy, and once it reaches products, the system had decreased in potential energy and increased in kinetic energy. This is why you saw the products moving much faster. It's not that the energy was created out of nowhere. That energy came from the decrease of potential energy that was stored in the relative position of particles inside the molecules. So that's important, because that will lead to what we will call the first law of thermodynamics, which is the conservation of energy. That's a take-home message. Energy, regardless of its form, is constant, provided there's no exchange, of course. So provided that the system does not lose energy to the exterior, energy will be constant. Okay. So we have a very graphical way to represent chemical reactions and their energy. This is what we call the metaphor of walking on valleys. From now on, you will think of a chemical reaction. You have reactants here, so that have higher potential energy, and you'll have products here that have lower potential energy. And so this will be, you can think of this valley, this graph as walking through valleys, and it has to go through something that we will call the transition state. Maybe you have heard about it. That's the peak of the mountain, if you will. But reactants and products exist in valleys of potential. So think always like that in these kind of forms where reactants, you can see the relative position of reactants and products. In this case, we can say that there will be some kinetic energy gained in form of temperature because reactants have a higher potential energy and the products have a lower potential energy. We will keep going back to these kind of representations. It's important that you keep in mind these graphs.